Hello, today we see the solution to the activity 3, which is on quadratic and cubic function. So the first exercise of the activity 3 is for each of these quadratic functions, first use differentiation to show whether they are concave up or down, and second determine the coordinates of the turning points. And then we have three different functions f, g, and h. So let's start with the first one. So we have to use differentiation to show whether the functions are concave up or down. And we recall here that if the second derivative of a function is positive, then the function is concave up, while if the second derivative of a function is negative, then it means that the function is concave down. So let's take the first function, which is f of x minus 3 to the power of 2 minus 8. So we solve the power of 2, it becomes x to the power of 2 plus 9 minus 6x minus 8. 9 minus 8 is plus 1, so this function becomes x to the power of 2 minus 6x plus 1. Now we compute the first derivative of this function, which is 2x minus 6, and then we compute the second derivative, which is just 2. So since the second derivative is positive, it means that this function is concave up. As a second point, we have to determine the coordinates of the turning points. We have our function, we have the derivative, the first derivative, and we recall that the turning or stationary points are the point at which the first derivative is equal to 0. So what we do is that we take the first derivative and we put it equal to 0. So 2x minus 6 equal to 0 is a first order equation, which becomes x equal to 3. And then we compute f of 3, so the value of the function when x is equal to 3. That is 3 to the power of 2 minus 6 that multiplies 3 plus 1. And this becomes equal to 9 minus 18 plus 1, which is equal to minus 8. Now we have the turning point. We know that the function is concave up, so we can sketch our function. So we draw the Cartesian plane. The turning point is x equal to 3 and y equal to minus 8. So it is the point that is shown with the circle. And this is just a sketch of the function that is concave up. Now we do exactly the same with the other two functions. So we have the function g, which is minus x to the power of 2 minus 2x minus 6. We compute the first derivative of this function because we want to see if the function is concave up or down. The first derivative is minus 2x to the power of 2 minus 1 minus 2, which is equal to minus 2x minus 2. The second derivative is equal to minus 2. So since the second derivative is negative, this means that the function is concave down. Now the turning point is the point at which the first derivative of the function is equal to 0. So we take the first derivative and we put it equal to 0. This is a first order equation, and the solution to this equation is 2x equal to 2, which means x equal to 1. Now we can compute the corresponding value of y, which is, if we do all the expressions, is minus 1 to the power of 2, minus 2 that multiplies minus 1, minus 6. This becomes 1 plus 2 minus 6, which is equal to minus 3. So now we have all the information and we can draw a sketch of the function. So we draw our Cartesian plane, and we know that the turning point is the point 1 minus 3, so this point here shown, and we can draw the function because we know that it's concave down. Now we have the third example, which is the function h, which is equal to x to the power of 2 plus 4x minus 5. The first derivative of this function is 2x to the power of 2 minus 1 plus 4, which becomes 2x plus 4. This means that the second derivative is equal to plus 2. So the second derivative is positive, which means that the function is concave up. To compute the turning point, I need to take the first derivative and put it equal to 0. The first derivative is 2x plus 4 equal to 0. The solution to this first order equation is 2x equals minus 4, which means x equal to minus 2. Now we compute the corresponding values of y, which is the function computed when x is equal to minus 2, and it becomes minus 2 to the power of 2 plus 4 that multiplies minus 2 minus 5. This is equal to 4 minus 8 minus 5, which is y equal to minus 9. So the turning point is the point minus 2 minus 9. So in our Cartesian plane, the turning point is the point minus 2 minus 9, so this point here, and the function is concave up, so we can draw a sketch of the function. The second exercise of activity 3 says, for each function, determine the stationary turning points, calculate the coordinates of the point of inflection, and draw a sketch of the shape of the graph. And the two functions are this function f and g. So let's start from the function f, and we want to determine the stationary points. To determine the stationary points, I have to compute the first derivative, which in this case is the function 3x to the power of 2 plus 2x. And the turning points are those points for which the first derivative is equal to 0. So I take the first derivative and I set it equal to 0. This is a second order equation. We can collect an x outside the parentheses, and this becomes x that multiplies 3x plus 2 equal to 0. This equation has two solutions. The first one for x equal to 0, at which correspond the value f of 0 of the function, which is equal to minus 12. The second solution is for 3x minus 2 equal to 0, which means that x is equal to minus 2/3. We can compute the value of the function when f is equal to minus 2/3, and this becomes minus 2/3 to the power of 3 plus minus 2/3 to the power of 2 minus 12, which is equal to minus 8 divided by 27 plus 4 divided by 9 minus 12. So this becomes minus 8 plus 4 that multiplies 3 minus 12 that multiplies 27, everything divided by 27. If we do the math, what comes out is minus 320 divided by 27, which is more or less equal to minus 11.8. So for this function, which is a cubic function, we have two stationary points. The first one is x equals 0, y equal to minus 12. The second one is x equal to minus 2/3, y equal to minus 320 divided by 27, which is more or less minus 11.8. Then for this function, we can also compute the point in which the concavity changes, or the point of inflection, and to do so I write the first derivative. I recall that the point of inflection is the point for which the second derivative is equal to 0. So the second derivative of this function is 6x plus 2. I put it equal to 0, and this corresponds to x equals to minus 1/3. This is the solution. And then I want to compute the corresponding y value when x is equal to minus 1/3. And this becomes equal to minus 1 divided by 27 plus 1 divided by 9 minus 12. And if we do the math, this becomes equal to minus 322 divided by 27, which is more or less equal to minus 11.9. So, to sum up, we have two stationary points and one point of inflection. Now we can draw our Cartesian plane. Since the points are a little bit weird, we have minus 12, minus 11.8, I zoomed in the Cartesian plane, and the values that you saw here are the values that I'm giving to the Cartesian plane points, okay? So the stationary point, the first one, is this point here, because it has an x equal to 0 and a y equals to minus 12. Then we have the second stationary point, which is for x equal to minus 2/3 and y equal to almost around minus 11.8. And then we have the inflection point, the point at which the curve changes its concavity, which has an x equal to minus 1/3 and a y equal to minus 11.9. I repeat here that here the Cartesian plane is not in scale. And we can then draw the function, recalling that the inflection point is the point where the function changes its concavity. So the function will be something similar to this. Okay, now we have to repeat the same thing with the second function, which is the function g of x equal to minus x to the power of 3 minus 3x to the power of 2 plus 9x minus 5. We can compute the first derivative of this function because we want to find the turning points. So the first derivative of this function is minus 3x to the power of 2 minus 6x plus 9. We recall that the turning points are the points at which the first derivative is equal to 0. So we take the first derivative and we set it equal to 0. This is a second order equation and can also be written in general terms in this way, where a, b, and c are the coefficients that in our case are a equal to minus 3, b equal to minus 6, and c equal to plus 9. So to solve this kind of equations, we need to recall the solution, the formula for the solution, which is this one. So we have two solutions to this equation, x1 and 2, and they are equal to minus b plus minus the square root of b to the power of 2 minus 4ac, everything divided by 2a. So we apply this formula, recalling that for us a is equal to minus 3, b is equal to minus 6, and c is equal to plus 9. So x12 becomes equal to minus 6 plus minus the square root of minus 6 to the power of 2 minus 4 that multiplies minus 3 that multiplies 9. Everything divided by 2 that multiplies minus 3. This is equal to 6 plus minus the square root of 36 plus 108, everything divided by minus 6. It becomes equal to 6 plus minus the square root of 144 divided by minus 6. The square root of 144 is 12, so this is equal to 6 plus minus 12 divided by minus 6. So we have two solutions, one where we use the minus and one where we use the plus. So x1, we use the minus, so it's equal to 6 minus 12, everything divided by minus 6. This is equal to minus 6 divided by minus 6, which is equal to plus 1. The second solution is with the plus, so x2, it's equal to 6 plus 12 divided by minus 6. This is equal to 18 divided by minus 6, which is equal to minus 3. So the turning points are 2. We have two turning points, one with x1 equal to 1 and one with x equal to minus 3. Now we compute the corresponding y values. So for the first one, we have to compute the function g at the point x equal to 1. So this is the values. So it becomes minus 1 to the power of 3, minus 3 that multiplies 1 to the power of 2, plus 9 that multiplies 1 minus 5. And if we do the math, this becomes minus 1 minus 3 plus 9 minus 5, which is equal to 0. The second turning point is for the value g x equal minus 3. So if we do the math, it becomes equal to plus 27 minus 27 minus 27 minus 5, which is equal to minus 32. So we have two stationary points, one for x equal 1 and y equal to 0, and the second one for x equal minus 3 and y equal to minus 32. Now, We want to compute also the point of inflection. To compute the point of inflection, we need to compute the second derivative and put it equal to 0. So the second derivative of the function g is minus 6x minus 6. We take this and we set it equal to 0. This is a first order equation, and the solution to this equation is x equal to minus 1. So the point of inflection as x equal to minus 1. To find the y-axis, we take the function and we substitute minus 1 to all the x values, and we find that g of minus 1 is equal to 1 minus 3 minus 9 minus 5, which is equal to minus 16. Good, now we have all the infos to draw the function. So we know that we have two stationary points. The first one is for x equal to 1 and y equal to 0. The second one is for x equal to minus 3 and y equal to minus 32. And one inflection point which is for x equal to minus 1 and y equal to minus 16. As in the example before, we have that the y values are very large, minus 32 and minus 16. So when I will draw the Cartesian plane here, I don't draw it in scale, so it's not in scale. So the first stationary point is for x equal 1, y equal 0, so is this point here. Then we have the second stationary point that is for x equal to minus 3, y equal to minus 32, so this point here. And then we have one inflection point which is for x equal to minus 1 and y equals to minus 16, so it's this point here. And now we can draw the function, recalling that the stationary points are points where the tangent is parallel to the x-axis, and the inflection point is the point where the curve changes its curvature. So the function will be something similar to this. And this is the two examples of activity 3.